Everyone, my name is Nikki and I'm a freshman at Penn and I'm one of the bioengineering teachers here. I'm really looking forward to getting to meet all of you. This week we're going to be talking about biomaterials. And biomaterials in short are really just any synthetic, so like created in a lab or design, or natural materials that are suitable for use in constructing artificial organs and prosthetics to replace either bone or tissue. And this is a really important part of bioengineering because this can be applied to just a bunch of things you probably already know about, such as medical implants, so stents or like heart valves. These can be mechanically designed, but then are used to function with like already existing biological systems. And then sutures, so different types of stitches. There's a bunch of different like synthetic biomaterials that can be created to use for this process. Regenerating tissue is a new area, and then drug delivery are just some of the ways in which biomaterials are used in day-to-day life. So in today's lab, we're going to be exploring some biomaterials. So later on, you'll see both a rubber band and some type of dough. And these both can function as biomaterials in sort and will be used to model stress and strain on muscles and just how body systems function. I hope you guys enjoy.
All right, hi guys. So I'm going to talk a little bit about stress and strain and how that applies to biomaterials. So what is stress? Stress is force applied per unit area. So it's basically asking like individual particles in a material, what are the forces that they're applying on other particles in the immediate vicinity? So the units of stress are pascals, and 1 pascal is equal to 1 Newton per meter squared, which is consistent with the force per unit area. And then our equation is over here, and its stress is equal to force per cross-sectional area. So there are a number of different types of stress. So there's compression, where you just push on both ends of something. There's tension, where you kind of pull on both ends. And then there's shear and other forces you can see here. So strain is the deformation of a material that is due to stress. So it's basically when you apply a force on some objects, how much does the length of the object change? So this is obviously unitless, because if you're doing change in length, which is going to be millimeters or meters or something, over the total length, which is going to be the same unit, they're going to cancel out. And our equation is epsilon is equal to delta over length. So that's going to be the strain is equal to the change in length over length. Okay. Young's modulus is the ability of a material to withstand forces without changes in length. So it's basically asking how much force causes how much change in length. And naturally, the unit's also going to be Pascal. And your Young's modulus is going to be E, because it's also called the elastic modulus. And that's going to be equal to stress over strain. So it's basically when you plot your stress versus your strain, it's going to be the slope of the line that you find. So we're going to look at some data now. So we have this, which is displacement versus force of a patellar tendon. So basically they took this tendon, put it in a machine that gradually applies force to one side, and then it measures the change in length of the material. So we have displacement versus force, but we want to get the elastic modulus. So what we need to do is convert it into strain and stress. So as we said before, strain is equal to displacement over the length. So we know the length of this material was originally 4 millimeters. So we're going to take each data point and divide it by 4 to get the strain. We're just going to drag that down to apply it to all of the data points. And we're going to do a similar thing to get the stress. So we know that stress is equal to force over cross-sectional area. And we know that the tendon was 0.6 millimeters in diameter. So that's 0.3 in the radius. So it's going to be 0.3 squared times pi. Just give a couple of sig figs. So that is going to calculate our stress. We can drag that down as well. Okay. So now what we have is a 2 by some number matrix that is our stress versus our strain. And if we plot this, the slope of the line will be our elastic modulus. So I've plotted that in MATLAB over here. So what you get here is not really what the graph that I showed you before looks like, where it's a nice straight line. So if you think about a biological material, here we have a tendon. There's going to be a point at which you can't stretch the tendon anymore without breaking the tendon, and that's how injuries happen. So if we look at this point up here, after this point, there's a marked decrease in the amount of force that you need to apply to get any displacement. And that is because at this point up here, the tendon breaks, and now the machine is pulling against nothing. So this is a product of it being a biological material. If you have a more man-made material, like maybe like a rubber band or something, it's not necessarily going to break. I guess that's a bad example because rubber bands do break. But if you have any like kind of typical material, maybe steel or something, those wouldn't break after like a normal amount of force applied to them. So here, because it's a biological material, it's going to break. So these types of graphs are split up into a number of regions. So if we look here, you can see that the graph is like almost linear. So this naturally is going to be called the linear region. And then this little region here, before it becomes linear, is called the tow region. So what would our elastic modulus be? It'll be the slope of the linear region, because that's when the material acts most like a normal material, where it's kind of a standard amount of force applied to change it in length. So what we want to do is pick the end of the linear region, so like maybe somewhere around here. So that's 0.08, so we'll just put that in here. And we're kind of just going to zoom in on this area. So now what we're going to do is we're going to kind of adjust this. And what this does is you can see this red line, as I move the slider to the right, is the red line gets closer to approximating what the blue data points actually show. And you can see our root mean squared error kind of changing. So we're going up now. We want it to be as small as possible. Right, so somewhere around here. So at this point, we can kind of see that this red line more or less approximates the blue data points. So the slope of this line would be our elastic modulus, and that's calculated here as 213. This is megapascals because we did newtons per millimeter rather than newton per meter, as we said. So this line here would be our linear modulus, and then this area here, as I said before, is going to be the tow region, which is the little area before it becomes straight. And since this is a tendon, we don't actually know for sure what causes this region, but tendons, you can kind of consider it as the individual fibers in the tendon kind of straightening out before they get stretched. So that's probably the cause of this tow region here. And then that break at the end is where the tendons themselves would break. So that is a little bit of an introduction into stress and strain and elastic modulus. If you have any questions, we'll have office hours on Sunday or Saturday, sorry.
Okay, so where do we see biomaterials? Well, really, biomaterials are in a lot of things. Some of the most obvious are, of course, these prosthetics, as you can see on the board. We have your good old evolution of replacement legs here, from wooden to fancy carbon fiber. And then, of course, we also have replacement joints, like the replacement hip or replacement knee joint. For a lot of people with, say, arthritis or with old age, they need to get a joint replaced, we can do that now. And we have to use biomaterials to decide what are we going to make the replacement hip or joint out of. Like, what kind of metal are we going to use? What kind of plastic are we going to use? How do we make sure that the material stands up to the regular wear and tear of use? What kind of stress is it going to undergo? And basically, how do we make sure that it works with the body, that doesn't, say, cause an immune reaction, that it fuses well with the bone and the surrounding tissue? So those are all questions that we ask when we make any sort of biomaterial, including the ones for these joints, and also for some other things, like some of the more common ones you could see are here. So these are dressings. This is a picture of normal dressings, but actually they're using biomaterial science, biomaterial engineering, to make dressings that can dissolve after you put them on in a couple of days. And this way, the wound can be kept cleaner and you'll be able to get plenty of air. You won't take the dressing off. Of course, here we see some more parts used in the placement joint, you see. You can see an actual picture of the metal, some of the implants they have here. And then, of course, this is a glucose sensor. And the glucose sensor is actually also biomaterials because you have to have, especially the sensor part, that actually checks the blood. Because you have to make sure that it does the right reaction with the blood to be able to check how much sugar is in it. But it's not just these mundane things biomaterials, not just joints and dressings and implants, also something pretty interesting, like this mechanical valve for the heart. So some people with heart disease, their heart valves are weak or they need to be propped up, and so you put in this mechanical valve in order to support the actual valve and make sure it stays open. And so what you need to consider here is how much pressure is going to be put on the valve from the mechanical valve, from the surrounding heart material, how much blood is going to flow through it every day. Is the material going to erode away at all? You got to better make sure that doesn't happen. Similar thing here with this stent. And if you guys don't know what a stent is, it's basically when you have a blockage in your artery, when you basically have a heart attack. One of the things they can do is that they push this stent in to prop the artery up and make sure blood can flow through it and try to remove the plaque. So with this stent, of course, many of the same questions. How much blood is flowing through it? How much pressure and stress and force is being put on the stent? And how do you make sure the material can stand up to that? And this last one, it's a little bit more experimental, but basically, this is an example where they took silver nanoparticles and they put them in a biopolymer. And what that created was this material that could actually help with wound healing. It promotes wound healing. So in really extreme case of say burn wounds or like of massive tissue damage, they're developing this material that they can put in there to basically help the wound heal faster. And it's a property of the combination of the biopolymer and the silver. And that's a really exciting field in biomaterials research. Now, speaking of biomaterials research, this is perhaps my favorite application of biomaterials. And this was a study from 2018, actually, but they were able to take these hydrogels and they were able to use them to help bone regenerate. Now, usually, you break a bone, it takes like a couple weeks to heal. It got put into the cast. But here, they were able to take these microbeads. So you can see this diagram right here. The microbeads, the fibers, and nanoparticles, they were able to put them all together in a matrix. And you can see some of the chemistry behind the matrix here. And they were able to implant that matrix into the damaged bone, and that would attract more osteogenic cells. And what these osteogenic cells that they use the matrix to build a new bone. And so this really was able to speed up wound healing, and it's pretty promising. If you guys want to take a look, you can check out the study. But what this shows is that really biomaterials is such a vast field, and it's really exciting.
In order to learn more about stress and strain and stuff like that, one of the examples that we have for you is just using dough. So dough you could just make by mixing flour and water together, and you'll just get like a nice lump of dough like this, and you'll be able to see the effects of elastic and plastic deformation. So if we take this example, if I were to just pull on the dough just a little bit, it'll go back and return to the original shape that it was. And this is an example of elastic deformation. However, if I pull on it too much, what you get is it won't return to the exact shape that it was before. And so that's an example of plastic deformation, which we talked about earlier. And so those are some of the examples of strain. And then so if we put too much stress on it and we pull up too much, it reaches that breaking point right here where the dough begins to just tear apart. And so that's the breaking point. And so if you want to learn more about materials, one of the examples that you can use is just with using dough.